Viewing the exam. I'm just started recording. Now let me go ahead and share. No, I don't want to exit minimize. Let me go ahead and share my screen. What did I send you?
Just an advertisement.
Seems like a bit of a long advertisement.
It's like a production story kind of thing.
Ah. It wasn't nice. What I sent you should have had something to do with pink lemonade.
I know. I wanted to watch the ad. I'm sorry.
Oh, okay. Sorry, I was just very confused. All right. So first off, for the exam, the way the exam works is going to be that I'm going to be taking into account that you can do some coding. Okay. And specifically, it's open book, open note, open internet. But if I find that basically people have like used Stack Overflow, like Chegg or some other cheating resource like that, and the rules will be specifically laid out, you know, I will be very angry. So normally I have all these hints. They're not going to really need to be there. I'll be there though for you to ask for clarification. Typically my exam's out of 105 points, but I can't really get it that way to work. So typically you'll have there'll be a way to, there'll be like up to 5 free points just for taking the exam. So, you know. Okay. So, oh, and finally, there will be, the last question is always just a 0-point question for you to upload any code for any of the previous problems. So if you are worried about the, you know, the text box not being great, you can upload it. Okay?
Okay.
So first off, this is a doubly linked list. Assume each node has a variable storing the memory location denoted by the letter of the node, right? So which of these is, so basically, please indicate the node being referenced by a chain of variables. So which node are we referring to? D.previous.previous.next.previous, so that's B. C.
For this one, they're all B, right?
Yep. C.next.previous.previous is also B. And here we can just do some canceling. So C.next.next.previous.previous, those cancel. And next.prev all cancel, so it's B. This should also let you know that basically that I am the type of person who will, on a for a series of true-false questions on an exam, just for ease of grading, I will make them all true or all false. So now, I don't have to do that because some of the stuff will auto-grade, but I am the type of person to do that on paper. Here, write a sequence of commands that will remove the tail of a doubly linked list. So here, you want to get the item before the tail, right? So get index or get size 2, get node at index size -2, and then use .next use .next is equal to .next on that. So essentially something that looks like this. What am I trying to? There's a lot of different ways to do it, by the way. So if your way is different, that's fine. Get node.
Do you mean like get rid of the last node, right?
Right. There's going to be less of these questions on the exam, by the way, and more towards the coding questions that are further into the exam. Okay. So these questions, mainly the thing is just to draw on the exam, what I'll be doing is I'll be giving you a list of so for this question.
Hold on,
this
sorry. About that remove question,
Mm-hmm.
the two commands that you put doesn't actually remove the last nodes, all right?
That wouldn't remove. Oh, and then we would have to say tail is equal to before. And that would remove the last node.
Oh, okay. With the
I mean, this would
garbage
remove it,
collector.
but this would set it so this removes it from the list, and this makes it so that the tail is the correct node.
Okay.
So next thing, so for this series of questions, though, what you'll get on the exam is a series of commands, okay, for a linked list, right? And then what I'll want you to do is choose the correct. I'll have like it'll be a multiple choice most likely where I ask you what is the correct state of, like, here's the linked list. It's initially A, B, C, D, E. Here's a bunch of commands. What is the way the linked list is currently it looks. So, using a linked list with 3 nodes, draw what happens as each line executes. So this would be good practice for that. Right, drawing. So drawing what happens as each line hits the tail. I can do that, but but I'm much more interested in getting to the harder questions, if that's okay with people. But I can also cover these. Do people want me to cover these questions?
Can we do
I'm
that
okay.
first? Then maybe if there's more time,
Oh, yeah.
go over these.
Is the answer key on Canvas? I think the answer key might be on Canvas. I mean, only put a couple of stuff on Canvas, so... This one's fairly straightforward. Suppose you have a list of integers. Write a method that finds the minimum and maximum and returns their sums regardless of the implementation of the list. Right? So it doesn't matter if it's a linked list or if it's a array list. So you can be guaranteed to get 2 questions that are like this. Okay.
So does that mean that it has to work for both linked lists and array lists, or that it can work for either?
Both, but it's gonna be able to work for both if you just use the list like I do.
Yeah.
So, yeah. If it says linked list, you should assume that on the actual exam, you can assume it's a link. It's going to be a singly linked. Okay.
Thank you.
Okay. Alt enter. There we go. So min max plus. So here we've got an integer maximum. Here we want to find the minimum, the maximum, and return their sums. So return min plus max, which was at the bottom of it. And now it's fairly straightforward to do that. For int I in list, so for every item in the list, if min is less than min, sorry, not if min is less than min, if I is less than min, min is equal to I, if I is greater than max, well, I'll learn how to type one of these days, max is equal to I. All right. So what's going on here? So first off, minimum is set to the maximum integer value, which is about 2 billion-ish. 2 billion and change. So by definition, pretty much any other number is going to be smaller than it. Okay? Make sense?
Mm-hmm.
That's why I set it up those ways. And same with max being set to min value, it's like negative 2 billion and change. And so almost anything will be bigger than that. And so what we're doing is that we're saying for each item in the list, if it's smaller than the minimum, then we found something smaller, so that should be the new minimum. If it's bigger than the maximum, it should be the new maximum, because it's bigger than that, so it's our new maximum. And just return their sum. Now, the question is, how much time does this take? What is the big O notation? What is the big O of your time complexity of the algorithm? That's one of my favorite questions to ask, even though it's only 2 points. Because it really depends on what you write. So here, this takes O of n time, be it a linked list or an array list. Now, with a linked list, that makes sense, right? Because you grab something at an index in constant time, right? And then you do a bunch of constant time checks over n items. Make sense so far for an array list?
Mm-hmm.
Now, with a linked list, you're going, wait a second. If I'm using the get method, that would take n time to grab something, and then n time to grab another item, and so why isn't it n squared? And the answer is because we're using a for each loop, which I haven't covered in class yet. If I use a for each loop with a linked list, it uses the iterator, which assumes you want to iterate through the list, and it will go from one node to the next node to the next node, saving your place, so that's an inefficient way to go through the list. So if you're iterating through a array list, if you're iterating through a linked list, you want to use, hold on one second. If you're iterating through a linked list, you want to use the for each loop like this, if you can. If you can. On the other hand, if we had done it like this, for int index is equal to 0, index is less than size, list.size, I plus plus, index plus plus, and then I'm just going to use bad names, but whatever. Int I is equal to list dot get I. Sorry, get index. Okay, which now it does the same thing as my previous implementation. The only difference is I have a get method here. This would take O of n time for the for an array list, but for a linked list, this would take O of n squared time. Does that make sense to everybody? Because we're using the get method here, and get for a linked list takes O of n time.
So if you use the for each method for an array list, is it still O of n time?
It is.
Okay.
Did you say that the get method for an array list is O of n?
It's constant time, my bad.
Oh, constant. Okay.
Get method for an array list is constant. Get for a linked list is O of n.
So for each loop is O of n time, and writing it out like this is O of n squared.
For a linked list, yes.
Okay. Thank you.
So the answer, what I'm trying to get to is that it depends it really depends on what you write and what your assumption are as to what the big O time will be. That's what it comes down to. All right, suppose we have some string, some list of words. Write a method called reverse words that returns a new list with all the strings reversed. So hello world nice becomes this. Okay. And it's a new list with all the strings reversed. So we're not replacing the old list. Or we're not making a new list. Sorry, we're not changing the old list. We're replacing everything in the new list. Sorry, we're not. My tongue isn't working. We are not changing things in the list. We're not changing the items in the list. Instead, we're creating a new list and adding things to that. List string I'm just going to make an array list here. It doesn't matter whether it's an array list or linked list. Really doesn't for this part. Okay. But now what I'm going to do is I'm going to again do a for each loop. For each string word in our list, what am I going to do? I'm going to need to reverse that and add it to the list. So string reversed is equal to... Now, if it was actually in Python, it's equal to whatever. Give me a second. And now list dot add reversed. And the indices would be the same because I'm just adding them one at a time after examining them one at a time.
Shouldn't it be output dot add?
Oh yes, it should be output dot add. I was just testing you, obviously.
I get an A star.
So here, reversed. If it was Python, this would be super easy because I could just do word like that. And in Python, that's enough to reverse it using slice notation. But it's not. Because Java and strings doesn't really give you useful methods. There's no reverse thing. So let's just do this sucker manually. Reversed is equal to empty string. And I'm a big fan of using for each loops because they're shorter. For car, letter, in, word. So here I'm just going through them in order. Okay, which is interesting because, wait a second, don't you need to go through them in reverse? And you're right, if I'd have to, so again, that gets to a lot of ways to do this. So here, what I'm going to do is I'm going to say reversed is equal to, let's see, letter plus reversed. And what that does is that for every letter, I add it to the front of what I already have. In effect, that's going to reverse it. Does that make sense? Just me being tricky here and being short here. But if that mental trick really is only, you can only come up with that if you already know that. So if you're not in the know for that mental trick, for I is equal to 0, I is less than word.length. And here, let's go in reverse, actually. Word.length -1. Start at the last index for the word. While I is greater than or equal to 0. I minus minus. So here I'm iterating through the reverse. Reversed is equal to, reverse plus equals word dot car at I. And now this again would be an Oven algorithm, where n is the number of strings. Make sense to everybody so far? I'm not hearing you, so I worry.
Yeah, I'm just writing down the answers. I had a
I
question
am
about
recording this, so.
Oh, true. I had a question about the for each loop that you were using earlier. So you said letter plus reverse for each letter in the word, letter
Yep.
plus reverse, right?
What I did
and
earlier.
I was,
Yeah, what I did earlier was this. Yes.
right, and I was thinking, so for each letter, so in the word hello, for example,
Yes.
letter would be H.
So
And
so I add H to the beginning of
oh, I get
reversed.
it.
Then I add E to the beginning, then I add L to the beginning, then L to the beginning, then O. So it becomes
Yeah,
Ole.
I got it. Thank you.
You want to try your
All right. So let's go ahead and look at this one. Suppose you have a method called delete list, which removes all items from the list, making it empty. This is an instance method inside of linked list, so you have access to head, tail, and the node class. Okay. One of my favorite questions here, because even though it's 3 points, because it's fairly straightforward. Because it does point out a bunch of points about this, so I'm just going to create a Java class. Linked list exam. So this is a linked list exam class. It's just going to take in an E. And I'm just going to throw in my node like I do normally. Okay? But again, this is unneeded if you're... Again, this is if you're trying to do a full industrial thing. What I could do is just simply jot it down, if right? Because the more you try to formally code, the longer it's going to take. So here, I can just write this. So to make the list null, to delete everything in the list, first thing I'm going to do is make the head equal to null. Then I'm also going to make the tail equal to null. Now this deletes everything in the list, right? We've no longer got memory locations pointing onto anything in the list. And then finally what I need to say is size is equal to 0. Make sense?
Do we have to like make any other variable point like for this dot next or anything like that?
Nope. Another way to do it, by the way, is while size is greater than 0, or rather, while this item's size is greater than 0, list or this dot remove, because we're talking about this item, this dot remove 0. Well, the size is greater than 0, remove the thing at the first index. Yes, Laser, what's up? I'm working. And in dire need of a coffee.
What do you want, Laser?
I have a question, but I mean, it's just a general linked list question.
Yes.
When we add and remove, when we made those methods, why do we have to change the size? Why isn't it just based on the list itself?
Because otherwise I'd have to count how many items are in the node. Sorry, in the list.
Okay.
And counting the number of items in a linked list takes O of n time.
I see. Okay.
So since size is such a useful operation to have, we keep track of the size. It also makes sure that other things will work.
Okay. So it's more of a counter than a...
Yeah.
Okay.
Yeah, we need to count the items just to know how many there are.
Okay.
With a linked list, it's a matter knowing the size is to know which part of the array we're allowed to fill up.
I see. Okay.
Otherwise, again, it would take O of n time to figure out how full it was.
Okay. So for an array list, for example, when you go like array list dot length or size.
Mm-hmm. Yeah. That gets you the number of items that are stored in the array list.
Okay.
Which is different than the capacity, which is the maximum numbers the internal array can hold before you have to reallocate. Okay. Write an instance method called count. Count iterates over a linked list and returns the number of times item occurs in the list. So again, you can do this in IntelliJ or whatever. I'm just going to do this. I'm just going to jot this guy down over here. So public int count an item. And so this is we're going to write this inside and this is an instance method again. So it's inside a specific list. Okay. So this is fairly straightforward. I'm going to say node. And you only want to use nodes inside instance methods, where you have access to the internals of the class. Node current is equal to head.
Can you really quickly say that last thing about when you want to use nodes and have access to the instances of the class?
Yep. I put it on the comments. It's an instance method, so you can use the head, tail, and node.
Okay.
When it's an instance method. In other words, when there's no static. Static means you can't use the head, the tail, and the node class because we don't have access to any of the other stuff.
You only sleep in your bed?
Okay. Thank you.
Because if it's a static method, then we aren't talking about any specific linked list. So, or the internals of any specific linked list. We can't use this. So, node current is equal to head. And this one's actually fairly straightforward. While current is not equal to null. We don't even have to use size here. While current is not equal to null. And I'm going to go ahead and say int count is equal to 0. Return count, because we're counting the number of times item occurs. So while current is not equal to null, if current dot item dot equals item, I'm going to go here. If that is true, and it's okay if you put in double equals on the exam, that's fine. If current item equals item, if those are equal, then count plus plus, increment the number of times we've seen it. Regardless of what we do, current is equal to current.next, which advances the current pointer. Right, so it's going to start at head, then move to index 1, then move to index 2, then move into index 3, and so on and so forth.
Could we use a for each here?
I mean, you could.
Tired, lazy.
You could use a for each loop there. And you could iterate through all the indices and stuff. But, I mean, honestly, it's just fairly easy. I like manipulating the nodes individually like this. Okay. Also, if you write a program, you can use it in future problems if you need to. What's the time complexity of this algorithm? Well, we hit each node exactly once, so it's O of n. Right? For each item in the list, what are we doing? We check the item, ask if it's null, then if it's not null, if it's null, we stop. Otherwise, we keep going and ask ourselves, okay, is check inside the item, do an increment, move to the next guy. Constant, constant, constant. And so this will happen a grand total of n times. All right. Let's see. Write a static method that takes in 2 sorted linked lists of integers. So we can assume that these linked lists of integers are sorted. Okay? And merges them into one sorted linked list and returns it.
Oh, so this is merge sort, basically.
That's exactly what this is. It's the merge portion of merge sort. So what we're going to do here is we're going to take list A, list B, which are both already sorted, and move them into one sorted list. So, we have to say linked list over here because it's a linked list. And we can assume that these are the linked lists that are built into Java. On the you'll be working with a specific class that I'm creating in the exam. So, or a specific new type of linked list that I'll be creating for the exam. Okay, sorted. Okay. So now what we've got to do is figure out how to take these 2 sorted items and move them together, or these 2 sorted lists, and put them together. And the most efficient way to do it is to basically say, hey, while list.a is greater than or equal to 0, while list.a is greater than list.a size greater than 0, while a is not empty and list b is not empty. What we're going to do, since we know they're sorted, we can compare the first two items. Okay? So we know in list A, so let's go ahead and write an example over here. 4, 7, 18, 2, 2, 10, 25. Okay, so these are our two lists that we're merging. If we compare the two items, first off, we know that 2 is greater than everything, it's less than everything else in its list because it's sorted. And 4 is less than everything else in its list because it's sorted. So, what we have to do is then, if we compare the first item over here, if this 2 is less than 4, if this 2 is less than the first item in here, then we also know, because this item is less than everything else in here, that 2 is smaller than everything and is in fact the smallest. Make sense? By comparing the first two, the first two items are always going to be the two smallest items, okay? Because these two things are sorted. And so if we figure out which one is smaller, then we know what the smallest item is. So, let's do that. If list.get, if list A is .get 0 is less than list B dot get 0, so if we get the two smallest items, so check them, and if A is smaller, sorted dot add list A dot remove 0. And what does that do? If A is the smaller item, take it away and put it into sorted. Otherwise, actually,
Could you do like sorted.add list.a and then maybe like a get at 0? Do you necessarily need to remove it from list A? Like, could you?
with the way I wrote it, you definitely want to remove it. Or at least, or with the way I am writing it. And then here's the reason why I want to do that.
Because of that while loop.
Mm-hmm.
Okay.
So here's what happens. I remove 2. And now we can just keep doing the check. Is 4 less than... Is 4 smaller or is 10 smaller? 4 is smaller. So we remove it. Is 7 smaller or is 10 smaller? 7 is smaller.
Okay.
10 or 18, 10 gets removed. 18 gets removed, and then we've hit a terminating condition. So we're left with one item still in there. And honestly, though, when we get through the for loop, we have no way of knowing if A is less than B, which is the empty one, okay? And we could write an if statement to do that, but honestly, it doesn't matter. What I'm going to use is a very nice method that's built into the Java linked lists and Java lists and the array lists, which is sorted.add all. I'm going to add all the items from that are left in list A. Sorted.add all list B. Now one of these two guys is going to be empty, right? Because that was what the terminating condition it was. Okay, one of these two guys is going to be empty. And then, so we add everything from list A. If it's empty, it doesn't do anything. Then we add everything from list B. If there's something there, it gets tacked onto the end of the list. And considering they're bigger than everything else, that's where it should be. Make sense?
Yep.
And by the way, I just simply have very efficient ways of writing this because I've been doing these problems for a while in class. So if you have a different way, it probably works. But this also takes O of n time if we assume that A and B are both like n divided by 2. If you're looking for a more appropriate amount, a more formally correct definition of how long this takes is it takes n plus m time. Or in other words, it takes big O of however big A is plus however big B is, because that's how many items we have. Okay. Write a method that reverses a doubly linked list. This method is an instance method for linked lists, so you can use the head and tail references and refer to the object using this keyword. So there's a bunch of ways you can do this. A ton of ways. They're all terrible. All right? Each and every one of these ways is terrible. So I'm going to do it in the cheaty face way that I like doing it. Okay? So we're going to reverse the linked list. Okay? It's not enough to just make the head the tail and the tail the head, because the pointers are still going to be messed up. Right? It's going to be thinking it should go one way when it should be going the other way. So here's what I'm going to do. I'm going to say linked list eTemp list is equal to a new linked list. By the way, I plan on this practice exam being harder than the actual exam, so I'm going to try to make the actual exam fairly straightforward online. Okay. There is one question that might be tricky, but linked list eTemp list is equal to a new linked list. Great. So what we're going to do is say for, I'm going to do the same thing I did here. While this dot size is greater than 0, I'm going to empty out this list. Or this list, as opposed to temp list. Temp list dot add this dot remove 0. And what this is going to do is that it's going to add everything back into temp list in order. So we haven't reversed it yet. We've just simply emptied out the current list and moved everything to a different list. Make sense?
Mm-hmm.
Now, what I can do now that this list is empty, I can say for I could do a for each loop, but I'll just continue doing the while loop because I like that. While
Couldn't you add the new list, everything from the new list into the temp list at 0?
Yep, that's exactly what I'm going to do.
Okay.
Well, list dot size is greater than 0. Or sorry, temp list dot size is greater than 0. So we're going to empty this sucker out. This dot add at index 0 temp list dot remove. Zero.
I think I have a remove.
Or no, it's just the cursor.
Mm-hmm. Okay, and now this will reverse the linked list. Now, actually, reversing a linked list is one of those interview questions that you get from big tech companies, because it's something that they can do to make it progressively more difficult. Because the follow up to this is, Okay. But can you reverse a linked list in place without using a temporary list? Okay. And that's a pain in the butt. Because what you got to do is basically you got to go through and make sure the next points to the previous and the previous points to what the next pointed to, which is tedious but doable. And then the follow-up to that is, well, now can you reverse a singly linked list in place without using a temporary variable? And that one's a pain, but it's actually doable if you know a trick, which is to basically have three node pointers. You have current, saved, and previous, and they advance all together. And you have the current point from one to the previous. And then finally it gets to the head, and you say what the head is. And so it just basically turns all the pointers around. But it holds on to the
Oh,
list,
I'm sorry.
but it holds on to the list in front of you so you don't lose it.
So wait, what would the head point to in that like scenario?
What was the tail?
Okay. Okay. Thank you.
But you only change the assignment of head and tail after you fix the direction everything goes, right?
In fact, normally I give it as a, In fact, normally I give that question as a, normally it's not, I don't think it really works in the online context, but normally I give it, here's a method or the pieces of it, please arrange the code into a reverse method. So, but as you can see, we could unscramble this and, give me 1 second. And the answer to that is, move this off. Apparently I don't have, in fact, the answers to that stored. That's okay. But I'm not going to give this question on the exam, but normally that's one I give on the exam. I will let you know that I do like dealing with sorted linked lists on the exam. So, questions that deal with this class. The sorted linked list. So keep that in mind. And if I like doing stuff with sorted linked lists, and over here we have a sorted linked list, right? That does an add method, then that should give you a pretty good hint as to what I would think would be worthwhile putting on the exam. Wink, wink, nod, nod, hint, hint.
Mm-hmm.
So suppose we had some new type of linked list called a sorted linked list, which is a linked list, but it keeps all the items sorted. As a result, when we add, we don't provide an index, as it just figures it out where it's supposed to go. So your task is to complete the add method for a sorted linked list shown below. This inserts a new item in such a way that it remains sorted. So here we've got 1, 2, 5. We add 4. If we call add 4, it's going to stuff it in right over here because that's where 4 goes in a sorted linked list. I'm just going to use a singly linked list, and I'm going to assume it's made of integers, so I don't have to use compare to. Here it's explicitly saying don't use the add method. You may not call the get node method, although you can rewrite it. We don't need it. And your solution must run in O of n time. That means we just need to hit every single node once, which means the get node really shouldn't be used anyway, since that takes O of n time to do. So to add a method. So to add an item, what we're going to do is we're going to use the current. Okay. So let's just think about like ways that this could go wrong immediately. Okay. So I'm going to go ahead and actually change. Let me delete this sucker. I'm going to put it into here. Okay. Create new Java class. Sorted linked list. And I'm just going to assume it holds integers rather than E. But because otherwise I'm going to go insane, right? So public, so I'm going to change this to int item. We're going to add this int item. Make sense to everybody?
Yep.
And then I'm going to need a node class.
Wait, so we will need to write a node class in that in that
Only if
question.
you plan on doing it in an IDE. Make sense what I mean?
Okay, yeah. I was still thinking of it like we were handwriting the exams.
Yeah, if you're handwriting it, which is why I expect it. If you're handwriting it, then there's no issue. Is it a private static class? I believe so. And then int item node next. Oh no, we need a constructor. We need public constructor. Public node int I this dot item equals I. There we go. Okay. For. So we're not going to use a for loop. First, let's think of ways that this immediately we can kind of trip over ourselves immediately. First and foremost is what if the current thing is null? So let's create a int head. Again, I'm overkilling this. I don't need the entire class definition. All I need is the method. I can assume head and tail already exist. Make sense? But over here, since I'm doing it in an IDE, like you might be doing it, I'm just going to go ahead and make a node head. Not even going to bother with a tail. Just going to do a head. Not even going to bother with the size. Going to keep it a really dumb linked list, okay? So, if first thing I should do is check if head is equal to null. Right? Don't have to do a out of bounds checks over here because we're adding an item. Doesn't matter what the item is. It's going to get stuck somewhere. Don't care what the index is. So if head is equal to null, this is the first thing we've ever added to the list. Head equals new node item. Make sense to everybody so far?
Yep.
And if we do care about the size, by the way, very simple. Int size equals 0. And then size plus plus after we're done with everything else. So if stuff does exist, then what I need to do is say node current is equal to new node. I'm sorry, not new node. It's equal to head, right? And then I'm going to say while current is not equal to null. Yeah. So it really depends on how you code it, whether you need current is equal to null or current.next is equal to null. Make sense?
Yep.
So while current is equal to null. So while current's not null, while we are still looking at something. Actually. Okay, so now thinking about this, right? Just like thinking about it for a couple seconds. I need to do current.next is equal to null. And the reason is because I need to look at the item ahead of me. Why? Because if I try to put myself before current, I'm not going to know what node that is. Unless I keep track of that. So there's a bunch of different ways to do this one. So here I'm going to say, so looks like I'm going to have to make another if condition. So else if, yeah, so I need 3 cases here. If item is less than head.item. So what happened over here? If the item is smaller than everything else in the list, and we know that because it's sorted. So if it's smaller than the head, it's smaller than everything else in the list. So it should come before everything else. So we create a new node, attach it to the head, and make that item the new first item. Otherwise, what are we going to do? We're going to say, okay, set current is equal to head. And while the next item is not null, what are we going to do? We are going to go and ask ourselves, okay, basically what we're going to ask ourselves is, should I put myself between current and current.next? That's what I'm going to ask myself. Okay. And I do that by saying if item is less than current.next.item. Not current.next, because I would have already, because if I try to check if I'm less than current, then I have to insert myself before current, but that means I need the pointer that points to current, and I don't have that. But I have the pointer that goes to current and current.next. So if item is less than current.next.item, okay, then that means I am going to go between current and current.next, which I'm just going to say node
Adding.
actually
Shouldn't you also have the condition that you're greater than current item or greater than or equal to?
what?
Shouldn't there also be a condition of being greater than or equal to current item?
No, we can already assume that I'm going to be greater than or equal to item, or greater than equal to the current item, because I've checked it. I would have checked it already.
Where?
Sorry. I'm sorry. I'm trying to remember the mathematic term. Proof by induction. So, I'm checking if I'm less than current over here. And head is going to be the first current. And so I check the item after head. So if I'm not smaller than that, that means I'm greater than or equal to it.
Okay.
So I could check, but it would be superfluous. All right. So let's see. So there's a couple ways to do this. Let me just see this. Well, current is equal to current.next. Yeah. So I'm gonna do this. I'm gonna do this, and then I'm gonna say wait what in just a second. Okay. So node.
Wait, what?
Give me a second. Node adding. This shouldn't be too confusing, this part. Okay. Create the new node. Hook it in. Okay. Attach it to current. Dot next. And have current point to you. And then I'm going to break it. I'm going to break out of this so the loop stops. Okay. But we have run it. But here's the wait what. What about if it's bigger than everything else in the list? Well, current.next is not equal to null. So if we get to the last item, then what do we do? And that's where we get into a bit of an issue. So here's what we do instead that actually fixes that. So what we do is that we advance current up to the point where we need to break, up to the point where we find the point for it. So we found the point for it, we stop looking. We create the node, connect it, and say current.next is equal to adding. So we connect it over here, where we say, hey, create the new node, attach that item to the next item. Sorry, attach that item to the item that's after me, and then attach the item that's before me to me. Now, if we had gotten to the end, right, and this loop ran the entire way, then, okay, doesn't matter. We're going to create a new node. Say adding.next is equal to null, which makes sense because if I'm the tail, if I'm the biggest thing, then that's going to come after me. And then current, which is the thing that's going to be before me, connects to me. This is by far more complicated than what's going to be on the exam. All right.
Okay.
But using the same structure would be very useful on the exam. Any questions about this one?
Why do you have the break?
Why do I have the break? To stop looking. Once I find the location I want to insert in, I stop it there. And the other reason is, like, if I'm inserting if I didn't have the break, let's go back to the way it was. If I didn't have this break, suppose I was inserting into a list of three. Suppose I was trying to insert a list into 3, 5, 5, 5, 5, 5. Okay? If I didn't have the break, I'd basically be saying, okay, 3. I'm on 3. I'm checking 5. 4 is less than 5, so I'm gonna put the 4 between 3 and 5. Okay, makes sense. But now without the break, I continue looking. Is 4 less than 5? Yes, so I'm gonna put a 4 between the 5 and 5. So let's go on to the next one. Oh. Now there's a, and actually it would get really bad because current would be the we'd actually have another 4. We'd check the 4, go on to the 5, and we'd keep basically attaching to the same 5 over and over again without the break. Does that make any sense or no?
Yeah.
All right. Analysis. So I guarantee you this question worth 20 points will be on the exam. Guarantee it. Okay? Guarantee that this question, a list can be implemented in other ways. Compare and contrast array list to a linked list. So let's go ahead and compare linked lists and array lists. And I want you on the exam to compare, and I'll put this out in 3 subproblems. I want you to analyze the difference between a linked list and array list in 3 different ways, okay? I want you to compare how they use memory, how they compare adding or removing, and how they compare with getting and setting. So let's talk about them. Let's talk about getting and setting because that's the easiest. For a linked list, to get an item, right, we have to iterate through the entire array to get there, right? The entire linked list to get there, right?
Mm-hmm.
Right, so if you want to find index 7, you have to start at, you can't just jump to the node at index 7. That doesn't work. You have to start at the head, then go to 1, then go to 2, then go to 3, then 4, then 5, then 6, then 7. And finally you get there because you're jumping around everywhere in memory. right? So there's nothing you can use. So there's nothing to get there. Oh, sorry, there's nothing to basically, there's no pattern, there's no rhyme or reason. They're just anywhere in memory. It's a big scavenger hunt. So it takes O of n time to find any index, and therefore find any item there. So get and set take O of n time. On the other hand, an array list makes use of basically a nice formula that that exists for arrays, which is that that basically the memory location. This is how arrays figure out how to get stuff out. Memory location is equal to the index. Is equal to the start location plus the index times so in other words, if it's a integer, it's going to look 4 bytes. It's going to look 4 bytes ahead. Make sense?
Mm-hmm.
It's going to be 4, or this is going to be equal to 4 bytes. So basically it uses this formula, and it takes constant time for it to do a formula because it doesn't matter how big the list is. It's just a number plus another number times another number. So that's the kind of computation that it does. It's a very simple way for it to get to memory. Or sorry, to get any point in memory. So getting and setting for an array list, constant time. Doesn't matter how big it is. It's able to jump to the right spot because it's using arrays. Okay. So here, the array list is the clear winner. Let me actually pull up my... Yeah, I didn't manage to finish this because... Alright. So for add and remove, on the other hand, that's a bit different. So for, in general, adding and removing any item to a linked list, to an array list, takes O of n time. Right? Because say you're at the front or the middle of an array list. Right? Adding to the front or middle, or removing from the front or the middle, you add an item, you have to shift n items over. Or n over 2. You remove, you have to shift n items over. Okay?
Mm-hmm.
On the only exception is when you add to the end or remove from the end, which takes constant time except under a specific condition. What's that condition?
The size is too small.
Right, so we would have to reallocate, right?
Yeah.
And reallocating takes O of n time. So the answer is it takes O of n time, except when you're adding or removing to the end, in which case it's constant, except if you're reallocating, in which case it takes O of n again. Linked lists, on the other hand, are a little less complex. If you have a head or a tail or another variable that's got the location of where you want to add or remove, then it's just a constant time. It's just the same lines over and over again, right? Just doesn't matter what to add an item to the head. All it is just here. Here's the node we're adding. Adding.next is equal to the head. Head is equal to the new node. Doesn't require shifting any items because we're just adding a new item to the chain. Okay? But if we're adding an item to the middle, yeah, the adding process itself, the physical act of adding, takes constant time. But to find the item, we have to take O of n time. So it's constant if you're heading to the head or tail, or O of n all other times. So the linked list has more constant time, so it's better to use there. Now let's talk about memory usage. All right? So what's a disadvantage of using an array list over an array?
Over an array or over a linked list?
Over an array. An array list over an array. And let's think in terms of memory.
Does an array list take more memory?
I mean, somewhat, but I mean, like, there is some overhead, but
Isn't an array just in one location, while an array list, each component is in different location, memory location?
well, with an array of primitives, that would be true, versus an array list. But if we're talking list versus an array list of objects, it's the same. Where every item in the internal array of an array list is a memory location of the item. So, but that's not right. Remember, everything in Java except for primitives is a memory location. It's a reference to the variable. So, but that's not really what's needed. Talk about reallocation. How does reallocation work with an array list?
You find something that's the size that you need. You find an area in memory that's the size that you need, and then you copy everything over, and then you delete the old one.
Okay, when do you reallocate?
When you are trying to add when the current size is not big enough.
Right, when your size would exceed your capacity.
Yeah.
Right? And how big is the new chunk of memory you need?
I believe it's twice as big.
Yep. Then that varies from implementation to implementation. Some people do 50% as big. We do twice as big. Okay. Or 150%, I should say.
The memory of an array is fixed, isn't it?
Yeah.
And then you have to physically go and change it.
That's true. So with an array list, though, let's think with reallocation versus how reallocate would affect an array list versus a linked list. If we reallocate, a linked list, an array list, say we've got a capacity of 1 million, or actually easier, let's say we've got a capacity of 1 million, and I add the million in first item, okay? What do? I find something 2 million, I create an array of 2 million, and that's the new array list, and copy everything over. Then add in the million in first item. Following me so far?
Mm-hmm.
Now suppose that million in first item is the last thing I add to this list. How much wasted memory how much memory are we wasting?
900,000.
999,999.
Yeah.
We are wasting that much blocks of memory. Right? So what the disadvantage of a array list is that if you are not careful, you can reallocate and waste a bunch of memory that way. Right? With just a bunch of unused slots in the array list. Does that make sense to everybody?
Mm-hmm.
Okay.
Yeah.
Now, there are methods and constructors inside array lists that help deal with this. Trim will take O of n time, and it will create a new array equal to the size. So basically, it's that you can use that to make sure you don't waste any additional memory. There's also a array list constructor where you can set the initial capacity to something other than 10. Okay. Now with regards to linked list, okay, we got to talk about overhead, right? The overhead for an array list is that each item in memory is actually a pointer. And a pointer is a reference. And that's a memory location, and that's either, let's just call it 4 bytes, okay?
So we're compiling 32-bit.
Yeah. Easier math right now. 4 bytes because there would be integers at that point. Okay. On the other hand, let's talk about a node. A node a node has 3 variables. Each node holds next, it holds previous, and it holds the memory location of the item.
What about if it's a singly linked list?
Let's see. If it's a singly linked list, yeah, give me a second. How'd that happen? Interesting. I'm just trying to figure out how to do a reverse arrow, but I don't think I can. So,
No, I think you can. Try less than minus minus.
that just makes it 2 equals like that. Does that. So previous, next, and the pointer. Okay, so we have previous, next, and then the pointer. I forgot what your question was.
I do too.
So here,
Question was,
basically,
what if it's a singly linked?
singly linked list. Then it doesn't change too much. It just means that we don't have our pointer over here. But for each item in the list, right, we'd be having, so first off, so here we have 6 nodes versus an array list of size 6, okay? Here we have 6 memory pointers, and here we have 6 memory pointers plus 6 nexts. So it's using twice as much overhead. And if you're doubly linked, you'd be using 3 times as much overhead. Does that make sense to people?
Mm-hmm.
So linked lists are a bit hungrier in terms of memory, but they're only going to use as much as you tell them to, whereas an array list might use more. So I guarantee this question will be on the exam. Okay?
Mm-hmm.
I guarantee it's worth 20 points, so it's worthwhile for you to know that. Also, you'll have about the linked list coding questions. I'll have 2 of them, and they will be on. I'm probably going to make this a fairly short exam. Now that I think about this, but the linked list coding question. Let's see. This guy over here. Sorry, not this guy. This guy over here, this linked list coding question for a sorted linked list, you can expect to have 2 questions that deal with the sorted linked list. Okay? And one of them on this exam was add, so you can kind of maybe figure out what it should be from by the inverse, you know?
Mm-hmm.
So, although I'll still find a way to surprise you there. And then I'll probably have 2 questions that are similar to, so let's go ahead and make this a fairly short exam, because when you're coding on the computer, it's very different, okay? So what we're going to do is that we are going to do 2 list questions, okay? They're going to be just like the questions on from assignment 2, okay? So around that kind of thing. Be sure to know what happens if you have to remove from a list as you're iterating over it, okay? Next. So 2 of those questions, 2 questions about sorted linked lists. So that would be 4 programming questions total, which I think is plenty. And then the remainder questions would be big O stuff, which would be given like, oh, no, we wouldn't need that. So then the 20 points for analysis. So 2 easy programming questions, 2 linked list program questions, analysis. Yeah, let me write this down. and this is subject to change on the actual exam, 20 points. Let's call it 40 points for sorted linked lists. Let's call it 20 for the and then let's call it 10 points for, because normally I have a printout I normally do. 10 points for here's code. What does it do? And then the remaining 5 points for that. 10 points for so 5 to 10 points depending on how everything flushes out of what the big O is up you wrote. Here's some code. What does it do? Multiple choice. Two problems for the array lists, and then 2 sorted linked lists problems, and that will be 30 to 40 points, depending on what I feel is right. I want to try to go lower on that. And I'll have a rubric on the exam so you can know, okay, if I do this, I get this many points. Make sense?
Mm-hmm.
And then you'll have at least 5 points of freebie points on the exam. Okay. So let me go ahead and stop recording.